Oh no, here comes a relativity skeptic. Why should we take anything I have to say seriously? Because I am a child math prodigy, according to Donald Coxeter, a famous Canadian mathematician. I'm in his book, listed as a child prodigy. Now, to a critical thinker, I don't think that would mean a whole lot. And to me, I don't think it means a whole lot because I know what I did to be in that book, and any kid could have done it if they just simply had some basic interest in geometry. Today's video, we're going to be looking one last time, hopefully, at special relativity. And in my last video, I kind of went over a lot more of how it's lacking experimental evidence. But in this video, I want to try to logically refute it in a way that's as simple as possible. Einstein himself said that if you understand an idea, you should be able to explain it to your grandmother. So maybe send this video to your grandmother and ask if ask if she understands this video, and hopefully your grandmother's not a physicist or something, right? All right, so this is a pretty standard explanation of special relativity. You're going to get this in pretty much every textbook, every YouTube video, probably every course too. And it goes something like this. So you have this rocket and it's traveling 10 kilometers an hour forward, and we have this basketball player dribbling this basketball. Now, of course, in the actual explanation, they use light, and we're going to get to light and explain how it's different with light. But I'm going to use a basketball because everyone's familiar with a basketball, and it's going to be ultra easy to understand, okay? So this guy's bouncing this basketball up and down 10 kilometers per hour like this. And I guess he has nothing better to do, so he's just doing it all day long, right? This is what he does because he's on this rocket and he's bored, all right? So the question is, from the perspective of the basketball player, how fast is the basketball traveling? Well, it's a pretty darn easy question. 10 kilometers per hour. Okay, so the next question is from the perspective of a stationary observer outside the rocket. So we have this guy and he's watching this rocket fly by him 10 kilometers per hour, right? From his perspective, how fast is he going to see this basketball traveling, right? Okay, so from the stationary perspective, he's going to see something like this. He's going to see this basketball bouncing up and down, and it's going to make this zigzag path. This stationary observer is going to see this zigzag path, right? If this basketball could paint outer space, let's pretend the basketball is covered in paint and you could paint the air, he would see this pattern getting splotched onto the air as the rocket moves forward. Let's say it takes the basketball 10 seconds to bounce from the top to the bottom of the rocket, okay? From the perspective of the person on the rocket, he's going to be seeing it travel this straight line distance in 10 seconds, right? From the stationary observer who's watching the rocket fly by, he's going to see it travel this distance in 10 seconds. This diagonal line is a longer distance than this straight line, so the basketball has to be moving faster. This is because speed is how much distance you can travel in a given time. Now, according to a bunch of junky science that we're not going to go into in this video, that I went into in my last video, everyone measures light to be the same speed regardless of their velocity. So what does that mean in plain English? It means that this person must measure the basketball moving 10 kilometers per hour. The person on the rocket must see it as moving 10, and the stationary observer also has to see the basketball moving 10 kilometers per hour on the rocket. Okay? Well, the only way the stationary observer is going to see this basketball moving 10 kilometers per hour on the rocket is if time itself slows down, right? Because otherwise this basketball has to speed up to move this longer distance. All right, so now we're going to start debunking special relativity, all right? So we have these two airplanes here and they're moving at different speeds. Plane 1 is traveling 10 kilometers per hour slower than plane 2. So this one here is faster. Plane 1 is moving 100 kilometers per hour relative to the floor of the Earth. So if you look down, the floor of the Earth is moving backwards 100 kilometers per hour from this plane's perspective. He's moving 100 kilometers per hour. That's pretty easy. Plane 2 is moving 200,110 kilometers per hour. What? What? No, shouldn't the answer be 110? Absolutely not. Okay, so what am I doing here? Am I on crack? What's going on? Okay. Well, the Earth is orbiting around the sun in this direction, 200,000 kilometers per hour, right? So this guy sees the Earth as moving 200,000 kilometers per hour, and this plane is moving 110 kilometers per hour faster than the Earth. So he adds the speed of the plane, which is 110 kilometers, to the speed of the Earth, and he comes up with this number of 200,110 kilometers per hour. Well, that actually makes some sense, but there's a very clear problem here, which is that we know plane 1 is only going 10 kilometers an hour slower than plane 2. So what mistake did we make here? Well, the mistake is very simple. We used different reference points to measure the speed. When we measured plane 1 speed, we measured it relative to the ground on the Earth. When we measured plane 2 speed, we measured it relative to a stationary perspective in outer space, right? We can't do that. We have to use the exact same reference point if we want to measure speed. So when we do that, now plane 1 moves to 200,100 kilometers per hour, and now we have this 10 kilometer per hour speed difference, and everything works out good. Or we can neutralize the speed of the Earth, cross that out of our math, and we're left with 100 and 110 relative to the floor of the Earth. Everything works when we use the same reference points. Now what I'm going to do here is I'm going to take this stationary tunnel. Okay, this is a stationary tunnel, and we're going to fly this rocket through it 10 kilometers per hour. And the walls of this tunnel touch the walls of the rocket. So the question is, for the stationary observer, I want him to look into the future and plot every single point that the basketball is going to hit the tunnel at, right? So he's going to look into the future and he's going to go, okay, well, the basketball is going to hit the tunnel here. Let's say that's where I start dribbling. Then as the ball bounces up, it's going to hit here, 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 here. As he looks into the future, these are the points he's going to agree where the basketball contacts the tunnel. And if we draw that line out, it's the exact same line that the stationary observer sees. When we use the same reference point, we get the exact same distance. But Albert Einstein reasons that the person on the rocket is actually stationary, and that it is the tunnel which is moving backwards 10 kilometers per hour. So when this rocket is moving forward 10 kilometers per hour, what he's experiencing is actually the tunnel moving backwards 10 kilometers per hour. Kind of like if you're driving a car, it looks like the floor of the Earth is moving backwards. All right, well, this doesn't create a problem either. If it is in fact the case that the person on the rocket is stationary and the tunnel's moving backwards, then this basketball is bouncing 10 kilometers per hour, whether you observe it from this position or this position. Why is that? Because we should be using the floor of the rocket as our reference point. When we use the same consistent reference point of the walls of the rocket, then both observers will measure 10 kilometers per hour. In Einstein's crazy system, in one measurement, he's declaring the rocket to be stationary, and in the other measurement, he's declaring the tunnel to be stationary. You can't do that. You have to either declare the rocket is stationary for both observers, or you have to declare that the tunnel is the stationary object for both observers. In one measurement, he's saying the floor of the rocket is the reference point, and in the other measurement, he's saying the floor of the tunnel is the reference point. These are different reference points. Now we're going to get to light, and this guy Domingo, you can find him on YouTube. He has this really great video. I'm going to link it in the video description. He explains exactly what's going on here with light, because light doesn't work the same as a basketball, okay? Light's a little bit different. Light is a wave, okay? So right here we have this airplane, and it's flying 1,000 kilometers per hour. Now this airplane is going to make sound come out in every direction, okay? So it's going to make this sound wave come out like this, all right? And the question is, how fast does this sound wave travel? Well, the answer is the sound is going to travel 1,000 kilometers per hour, which is the speed of sound this way and this way, all right? And what I mean by that is the sound wave isn't going to be traveling 2,000 kilometers per hour in this direction, because we add the speed of the sound to the speed of the plane. Make sense? And this can easily be proven by a sonic boom.
Sonic boom! Sonic boom!
So let's say this plane was moving 2,000 kilometers per hour, then the speed of sound would only be moving 1,000 kilometers per hour, and we will hear this sonic boom because sound falls behind the plane. It can't move at the same speed of the plane, so the sound comes after. So now here we have this rocket, and c is the speed of light. This rocket is traveling at near c, so almost the speed of light, and we have this light beam bouncing up and down, just like the basketball before. Einstein reasons that from the stationary perspective, they'll see this zigzag line as this rocket moves forward, right? And from being on the rocket, you see it moving up and down. Now, waves work different than the basketball because with waves, we don't add the speed of the plane to the speed of the wave. And the same thing's true here. We don't add the speed of the rocket to the speed of light. So this rocket actually gives the light no lateral momentum. So what we would actually see is the beam of light moving as follows, just up and down. The horizontal momentum of the rocket does not affect the beam of light, so we just see it moving up and down. So actually Einstein's logic is backwards. If we're on the rocket, we should be seeing the zigzag pattern, and from the stationary perspective, he'll just see this light moving up and down. And well, then isn't Einstein's argument true, but just reverse? This guy will measure the speed of light to be slower because it's just moving up and down, and the person on the rocket is seeing it move backwards. Well, no, it's the exact same thing as before. When we declare the same reference point, right? When we declare, for example, the stationary observer's platform to be the reference point, then we'll both see the beam of light bouncing up and down. Or if we declare the walls of the rocket to be our reference point, then we're both going to see this zigzag motion, and we're both going to measure the same speed of light. All right, so there you have it. Does my logic make sense? Do you see any problems with my logic, or is that a pretty good argument? I think that deflates relativity pretty well here.